Imagine a world where a single, almost invisible tweak to the architecture of solar cells could ignite an era of affordable, ultra-efficient clean energy. Picture a discovery so profound that it might accelerate humanity's escape from fossil fuels, reshape global energy markets, and even alter the balance of power among nations. This is not science fiction. It is the reality unfolding in laboratories today. Welcome to a deep dive into one of the most pivotal breakthroughs in solar technology, the rise of titanium dioxide nanorods and the precise control of their arrangement, a feat that could redefine how we capture and use the power of the sun. Let's rewind for a moment. Solar energy has always held the promise of abundance, a virtually limitless resource shining down on every corner of the globe. Yet harnessing this energy efficiently and affordably has never been straightforward. Since the birth of the first silicon solar cell in the middle of the 20th century, scientists and engineers have waged a relentless campaign to break through the barriers of efficiency, cost, and scalability. Consider the journey. Early solar panels, bulky and expensive, powered satellites, and niche scientific installations. The 1970s oil crises galvanized research. But for decades, solar remained a premium option. Only in the past 2 decades, as silicon manufacturing matured and economies of scale kicked in, did solar reach parity with traditional energy sources in many markets. Still, even today, the world's energy mix is dominated by coal, oil, and natural gas. Solar must become not just competitive, but overwhelmingly superior, more efficient, cheaper, and adaptable to diverse environments, if it is to fulfill its promise. This is where the microscopic world of nanotechnology enters the scene. At the heart of every solar cell lies a deceptively simple task: turn as much sunlight as possible into usable electricity. But sunlight is tricky. Photons can bounce, scatter, or be absorbed in the wrong places. Traditional materials like crystalline silicon have physical limits. To push beyond these, scientists have begun to play at the atomic and molecular scale, engineering materials whose properties can be tuned with almost magical precision. Among the stars of this nanoscale revolution is titanium dioxide, often abbreviated as titanium-4 oxide. This compound, known to most as a white pigment in paint or sunscreen, has emerged as a critical ingredient in advanced solar cells, in particular when shaped into nanorods. Tiny pillars so small that tens of thousands could fit across a single strand of human hair. Titanium dioxide unlocks a host of remarkable properties. These nanorods act like superhighways for electrons, shuttling charge with minimal resistance and maximizing the absorption of sunlight. Dr. Emily Carter, a renowned materials scientist from Princeton University, eloquently summarizes the potential here. Titanium dioxide nanorods offer a cost-effective pathway to enhance light trapping in thin-film solar cells. They combine Earth abundance, stability, and performance in a way that few other materials can. Yet, as with so many scientific advances, the devil is in the details. For years, the dream of widespread nanorod-based solar cells was held hostage by a stubborn challenge: how to control the distance between these rods. Imagine trying to plant a field of perfectly spaced trees, but every time you adjusted the distance, the trees themselves changed size or shape. In nanotechnology, this interplay between spacing and morphology is even more delicate. If the rods are too close, electrons can get trapped or recombine before doing useful work. If they are too far apart, sunlight slips through the gaps, wasted. Traditional fabrication methods, whether chemical vapor deposition, hydrothermal growth, or spin coating, tend to link spacing and size. This trade-off has frustrated scientists and engineers for decades. The inability to independently tune these parameters has limited efficiency gains and made scaling up to industrial production a logistical nightmare. Everything changed when a team of Chinese researchers, led by Professor Wang Mingtai at the Hefei Institutes of Physical Science, announced a breakthrough. Through an ingenious refinement of the nanorod growth process, specifically by adjusting the hydrolysis step during precursor film formation, they discovered a way to fine-tune the spacing between titanium dioxide nanorods without altering their diameter or height. Instead of the rods growing haphazardly or in clumps, they now stand in precise, uniform arrays, almost like soldiers on parade. This subtle shift, invisible to the naked eye, is revolutionary at the nanoscale. The secret lies in the formation of smaller anatase nanoparticles, which, during subsequent hydrothermal treatment, convert into rutile seeds. These seeds, guide the growth of perfectly aligned, evenly spaced nanorods. By controlling the density of these seeds, the researchers can dictate rod spacing with astonishing precision. But what does this mean in practice? When the Hefei team incorporated their optimized nanorod arrays into copper indium sulfide solar cells, a type of thin-film solar cell prized for its low cost and flexibility, the results were startling. Power conversion efficiency soared past 10%, with a record peak of 10.44%. To put this in perspective, these are numbers previously thought unattainable for such low-cost materials. Professor Henry Snaith of Oxford University, a global leader in photovoltaic research, was quick to recognize the significance. This approach can improve electron transport with minimal material cost, a real breakthrough for the industry. The ability to optimize architecture without compromising material integrity is a game-changer. The innovation doesn't stop with efficiency. By providing a new framework for designing nanostructures, what the researchers call a volume surface density model, they have laid the groundwork for a new generation of solar devices, not just in energy, but also in broader optoelectronic applications. Imagine light sensors, photodetectors, and even next-generation LEDs benefiting from this precise nanoscale engineering. So where do we go from here? As with any disruptive technology, the road from laboratory discovery to global adoption is fraught with hurdles. The first, and perhaps most daunting challenge, is scalability. It is one thing to grow perfect nanorod arrays on a postage stamp-sized test device in a controlled lab environment. It is quite another to replicate this feat over square kilometers of solar panels destined for rooftops, deserts, and floating platforms around the world. Scaling up demands not only technical prowess, but also industrial agility. Manufacturers must source ultra-pure precursors, control reaction conditions to fractions of a degree, and maintain uniformity across thousands of production runs. Chemical suppliers must adapt to new purity standards. Quality control systems must detect and correct minute deviations in rod spacing that could cripple performance. And all of this must be achieved at a price point that keeps solar competitive with ever-cheaper fossil fuels. There is also the question of durability. Solar panels are expected to last 20 years or more, enduring cycles of intense heat, biting cold, rain, hail, and dust storms. As Dr. Peter Werfel from the Fraunhofer Institute for Solar Energy Systems cautions, stability is the last frontier. Without it, excitement fades fast. New materials and architectures must prove their mettle in the real world, not just in the lab. Some early studies are promising. Annealing titanium dioxide nanorods in a hydrogen-rich atmosphere, for instance, has been shown to boost their conductivity and resilience. Other research has combined nanorods with carbon nanotubes, yielding films with superior electron transport and lower recombination rates, a hint that hybrid approaches might further extend lifespan and performance. Behind these technical hurdles loom even larger economic and geopolitical questions. The global solar industry is a battleground, with China, the United States, the European Union, and emerging economies all vying for leadership. If titanium dioxide nanorod technology proves scalable, it could upend existing supply chains. Titanium dioxide is far more abundant than the rare earth elements used in some advanced solar cells, meaning countries with access to basic minerals and chemical know-how could leapfrog into the lead. But there are risks too. What happens if the price of silicon, the current workhorse of the solar industry, collapses due to oversupply or new extraction methods? Will companies be willing to invest billions in retooling factories for nanorod architectures? Or will only a handful of forward-thinking firms take the plunge? How will trade tensions, environmental regulations, and intellectual property battles shape the rollout of these new cells? There are also environmental stakes. One reason titanium dioxide is so attractive is its benign nature. Unlike cadmium or lead-based compounds, which raise serious health and disposal concerns, titanium dioxide is non-toxic and abundant. The ability to manufacture high-performance solar cells without rare or hazardous elements could make solar truly sustainable, not just for wealthy nations, but for every community on Earth. Let's imagine some of the scenarios that could unfold if this breakthrough technique moves from the realm of research to everyday reality. In the most optimistic vision, within the next 5 to 10 years, solar panels based on precisely engineered titanium dioxide nanorods begin rolling off production lines in China, Europe, and North America. Thanks to their superior efficiency and low material costs, these panels quickly find homes not just on suburban rooftops, but also as transparent coatings on skyscraper windows, integrated into the siding of houses, and even woven into flexible fabrics for tents and backpacks. Rural villages in sub-Saharan Africa or Southeast Asia, previously beyond the reach of grid electricity, leapfrog straight to distributed solar powered by affordable, durable panels. Urban centers see the rise of building-integrated photovoltaics, where every surface is an energy generator. For industry, the impact is profound. Energy-intensive factories, data centers, and transport hubs slash their energy bills and carbon footprints. Utilities rethink grid design, integrating more distributed generation and storage. Governments accelerate the retirement of coal and gas plants, spurred by the falling cost of clean energy. But the journey will not be without turbulence. Scaling up production might reveal new bottlenecks, whether in sourcing ultra-pure precursors, managing waste streams, or ensuring quality control. Some companies will stumble, while others, nimble and innovative, will sprint ahead. Early adopters may face teething problems as the technology matures, much like the initial waves of wind and solar installations in the early 2000s. Investors and entrepreneurs, take note. History suggests that those who move early and learn fast can capture enormous value. Consider how First Solar, a pioneer in thin-film photovoltaics, or Tesla, with its audacious bet on gigafactories, reshaped their industries. The next wave of disruptors may well be startups or established manufacturers willing to bet on the promise of nanorod-based solar technology. For ordinary consumers, the benefits could be equally transformative. Imagine walking into your local hardware store a decade from now and choosing from a range of solar products. Flexible panels for your balcony, transparent films for your car's sunroof, or even smart fabrics that charge your devices as you walk. Home builders might offer integrated solar windows and roofs as standard features. For renters and homeowners alike, the barriers to clean energy adoption could shrink dramatically. What about the technology's ultimate potential? Researchers are already exploring ways to push efficiencies even higher by combining titanium dioxide nanorods with other advanced materials. For example, pairing nanorods with perovskite layers, a promising but still maturing class of solar absorbers, could yield tandem solar cells with laboratory efficiencies exceeding 25%. This is more than double the typical efficiency of commercial solar panels today. Some experts envision a future where solar cell efficiencies routinely surpass 30%, making solar the default choice for new power generation worldwide. And the environmental benefits go even further. By reducing dependence on scarce or toxic elements, nanorod-enhanced solar cells could dramatically lower the ecological footprint of solar manufacturing. As Dr. Michael Gratzel, inventor of the dye-sensitized solar cell, points out, we finally have a pathway to sustainable, high-performance photovoltaics using only Earth-abundant materials. This is not just an incremental step, it is a paradigm shift. Of course, challenges remain. The long-term stability of nanorod-based devices under harsh outdoor conditions is still being tested. Material degradation, interface chemistry, and encapsulation methods all need further refinement. Policymakers and regulators must ensure that new manufacturing processes meet environmental and labor standards. And the industry as a whole must guard against the mistakes of the past, overpromising, underdelivering, or failing to anticipate secondary effects like electronic waste or land use. Yet, the convergence of nanotechnology and renewable energy is opening doors once thought permanently closed. For the first time, we have the tools to manipulate energy conversion at the atomic level, maximizing every photon, every electron, every opportunity for sustainability. So what does this mean for you? Whether you are a student, a homeowner, an entrepreneur, or simply a concerned citizen, the implications are profound. The cost of clean energy could fall even further, making it accessible to billions more people. The vision of a world powered by the sun, where energy is democratic, abundant, and clean edges closer to reality, with every breakthrough at the nanoscale. For those passionate about sustainability, the lesson is clear. Never underestimate the power of tiny changes at the atomic scale. Decades of incremental progress, punctuated by moments of true discovery, have brought us to this threshold. Each tweak, like the spacing of a nanorod or the chemistry of a seed layer, pushes us further towards mainstream adoption and a lower carbon future. Will this Chinese breakthrough become the missing link that finally tips the balance, catapulting solar energy to dominance? The answer is not yet certain. Technical challenges, market adoption, and policy decisions will all play decisive roles in shaping the outcome. But as Dr. Emily Carter notes, We are witnessing a moment when nanotech and renewable energy converge. That has never happened at this scale before. Here's something many headlines miss. While efficiency grabs the spotlight, the true game-changer could be sustainability. Titanium dioxide is so abundant that we could power civilization for centuries without depleting the planet's resources. This is a quiet revolution in resource management, one that may be just as important as any leap in technical performance. In summary, the breakthrough in controlling titanium dioxide nanorod spacing is more than a laboratory curiosity. It is a beacon for the future of solar energy. A future where efficiency, affordability, and sustainability move hand in hand. The journey from lab bench to rooftop, from research paper to real-world impact, will be complex and fraught with hurdles. But the prize, clean, abundant energy for all, is worth every effort. If you found this exploration inspiring, do not forget to subscribe and tap that notification bell. We will keep tracking the most exciting advances in energy and technology, bringing you stories that matter. What do you think? Will nanorod-driven solar cells become part of your daily life? Could the next revolution in energy begin with a structure thinner than a human hair? Let us know your thoughts in the comments below.